So I'll be talking about containers on Theta and Theta GPU. Hopefully everyone got here we go, sharing my screen. Hopefully everyone received a message via Slack about installing Docker on your local machine, somewhere that you have sudo access, I believe, is required for building Docker images. On our systems at ALCF, we run Singularity, which is an HPC-oriented container framework that has the security of a multi-tenant cluster in mind in its implementation, whereas Docker still has some security issues when you're running a system where multiple users are on your system with different permissions and capabilities that lead to issues that we could not run Docker on our systems directly. So we use Singularity, but Singularity can derive containers from Docker images. And so the easiest way to build images to run on Theta is using Docker on your local system. And so I'll give some examples and some rules to follow when you're doing that. I'm down in the O3 containers directory. Please feel free to interrupt or insert questions into the containers Slack channel. So if you're not familiar, containers are slightly different than virtual machines in the sense that they are lighter weight. Virtual machines essentially have your infrastructure, which in this case is like the hardware of the computer node. So, you know, your CPU, your memory, network, so on. And in a virtual machine architecture, you have a hypervisor that runs on top of that and then hosts these full virtual machines, which have an entire operating system with hardware virtualized as well, contained in here. So you're, it's a full ground up implementation of the operating system, and even some of the hardware has been is being virtualized as software in these images here, and so a virtual machine can be a little less performant because of all of that, and which has led people in the direction of using containers, especially in the cloud. And a container shares the host operating system on the compute node, and then runs something like Docker or Singularity inside that operating system. And then you have your apps, the applications you want to be running in a contained environment where you might have things like your Python installation or your system, your build libraries for GCC and all your GNU or maybe your CUDA libraries, but all the operating system needs come from the local host system. You don't have to carry those, and you're also sharing all the hardware in a normal way, so that you don't have to virtualize your hardware. This tends to be lighter weight, tends to lead to better performance, and tends to be enough for our use cases. Usually you don't need hardware virtualization unless you're really worried about historical, keeping things historically reproduceable. So at the ALCF, like I said, we use Singularity, and we recommend running Docker on your local machine, building your containers there if you can, and then those get uploaded to the Docker Hub, which is Docker's public repo. It's like GitHub, but for containers. And then you can pull those into the ALCF on a login node, and I'll step through how we do that. I'm not going to reproduce a lot of Docker, pre-existing Docker or Singularity documentation for that matter, just enough to get us through the tutorial here. But I include links to the documentation that's helpful. If you need to get more nitty-gritty about how you're building your environments, you might need some more details about what we're going to go over. So first, obviously, you need Docker installed on your system. So hopefully everyone that wants to follow along has done that. We have some examples in this local source directory here. So these Docker files are the recipes. And then we have source code that we're going to build. We'll build the C code into an MPI application. And then we have a Python MPI for Pi example just to show that. And then we have some run scripts, some submission scripts down here in the Theta and Theta GPU directories, which we'll dive into. So let's get started. So we're going to start with the Docker file that's in this local directory. And that Docker file is geared toward Theta, the KNL nodes. And if you look at this file, and I've brought it out here, but I'll just show this to you. It's one big script with lots of different pieces. And now we'll go through those pieces piece by piece. The first thing you're going to do is you're going to start with a base image to build your container on top of. And in this case, we're going to grab an Ubuntu image, 20.04. This is sitting in Docker's main Docker Hub repo, so we can just give it this name. And it will grab that image, download it, and then all of our installation will go on top of that image, and then it will generate a new one that contains everything, the Ubuntu installation and everything we've added on top. So the first thing we're going to do is we're going to run this command. So we use this run keyword. So we use this from keyword, which tells us where we're starting from. And now we're going to run some things. We're going to run apt-get. If you're familiar with Ubuntu, this is how you install packages from the command line. So this is like running a bash command in the shell. And so we're going to just run a generic update command. So we want everything in Ubuntu to be updated. Then we're going to install some build essentials. So this is just a shorthand for G++, GCC, all those things that we need to build C code. We have some additional networking, and we've got some Fortran. We want wget in there because that tends to be helpful. And then for Python, we need to install Python 3. So we install those. So these are being installed into the Ubuntu operating system image that we downloaded. Now we're going to create a work directory at /mpitch. Theta KNLs all use Intel npitch, Cray npitch for running MPI. And it's important that we match the MPI library on the local system so that we can use the local MPI to operate our high-speed interconnect when we're writing our program. So we're going to declare some shorthand variables here. And now we're going to run, again, this shell script where we're going to wget our mpitch tarball from the web. So we download that tarball. We untar it. Okay. And we're just going to untar it directly into this /mpitch directory, which is where we're sitting. And then we're going to run the installation directions. If you go to the mpitch website. It tells you how to install mpitch, and it's just the usual /configure installation, and then you run make install. And it's important to point out this configuration option right here, disable wrapper RPath. By default, this configure command sets up our build so that it tells our compiled binaries. So if we were ever to build against mpitch, any binary that we build would automatically know exactly where to find the MPI library. And in this case, MPI is inside of our container, but we want to, when we run our container on Theta, we don't want it to use our container's MPI. We want to use Theta's MPI so that we can use the high-speed interconnect to communicate. And to do that, we want our binary to grab the library from our Theta file system, not from the container. And by default, if you don't include this flag, by default, it will make sure that any binary that is compiled against MPI always gets the same library, which usually makes sense, that you built it with. And in this case, it's the one in the container, but we don't want that. So we include this flag to tell it, grab the library for MPI from the LD library path from the environment, not from, don't force the binary to a specific path. And then we're also going to add to our local environment while we're building. Notice the difference here. These args are used, can be used in these commands, but we want to update our environment variables, path and LD library path to point at our mpitch install in this case. And then we're going to run pip install MPI for Pi for our Python example. MPI for Pi is just a Python wrapper for MPI calls. And this actually does some compilation against our MPI installation container, which is why we need these environments. We're going to create a new working directory called user. And then we're going to copy our source code. You remember that .c file and the Python file from the hello world example that sits up here. Local source. We're going to copy these two files into our images base path user/source and /user. We're going to bring that submit script in here. And then we're going to run this, and we're going to tell it to run an MPI CC. So it's going to build an MPI application out of this MPI hello world. And you can go take a look at that. It's very simple MPI code that just prints rank and size and the host information. And then we can provide an entry point for our images. And in this case, we're using this submit script, and the submit script is really just running both of these examples. So it runs MPI run for the MPI world, and then also for the Python example as well. We actually won't use that in this tutorial, but it's here just to demonstrate that there's this thing called an entry point in your recipe. And that really just sets in Docker and in Singularity, when you run Docker on the command line, you can type in Docker run and then the container name. You don't have to provide any other information. And what that means is it's going to run whatever you define in this entry point. So in this case, it's going to run that submit script in the container environment. Otherwise, we can do anything else that we want inside the container's environment by running docker exec, the container name, and then the command. So if we wanted to do anything but this, we'd have to use the exec command. Okay, so we have our Docker recipe. pretty straightforward. And now we're going to build that container or that image. And I point out here that you're going to hear these terms images and containers. In Docker speak, an image is the thing, is a static representation of the environment. So it's like all the operating system files, all the things you installed, and it's static, it's constant. Now I'm going to launch an instance of my image, and then it becomes a container because it's a running environment based on my image. I can do Docker exec, I can call Docker exec and then the container and then bash and enter an interactive shell in my containers environment. And I can do things in that environment like install new stuff, or add files and folders. But the problem is when I destroy that container, when I close that container, all those things go away unless I create a new base image based on what I changed. So my image is static. A container is a running instance of my image. Hopefully that makes sense. Right, so Alfred asks, does Docker run the installation commands every time a Docker file is run? No, so once you create an image, like I said, that's static. And then I'm gonna say Docker run, and then the image name. And that's gonna start a container based on my image. I can always update, I can use a running container and I can tell Docker, take that container and I want that container to be my new version, my latest version of image so-and-so, right? So I can use a running container as a way to update the static image over time if I like. Okay, I thought that it was helpful to point out that sort of nomenclature that they use there. Okay, so you're going to want to have a Docker Hub account for this to go through the tutorial. And once you have an account, you're going to be able to create a repository. So here I just create an example place to store my images. So ALCF CWP, although an acronym should be CPW for the Computing Performance Workshop, but I swapped those, but anyway. And so then you just create that, and it will show you how to push to this repo. It shows you the command on that window, but we'll go through it. So now we have our Docker recipe and we can build our image. So the first thing we do is we cd into the O3 containers directory on our local system. And then we can run docker build /t, which just means I'm going to tag this image that I'm building. I'm going to tag that image with my username, that repo. It's the same that pops up here, except I'm going to change tag name. If you caught that, it goes by quickly. So after I create the repository, you can see right here. So I'm going to use that example there. And then I'm going to name this, I'm going to tag this image with the latest. And so tagging works same as GitHub. This could be any string that I want, really. But in the Docker Hub world, traditionally you use latest to be the latest version of your image. So maybe before you commit to latest, maybe you would tag it first as version 1, and then tag it again as version latest, and so on and so forth. And so the next thing I want to do, since I'm in this O3 containers folder, there's a path .local. So this is this folder here. And this folder has a Docker file in it. Now, by default, the build command in Docker is going to look for a file named Docker file with this name. It's going to ignore this one here, which I made specifically for Theta GPU, and we'll cover in a moment. But so without specifying anything, it will look for that Docker file in /local, and it will build that recipe. Here I'm explaining the tags. Here I'm talking about the local file and how it defines which recipe it's going to run. Now, if I wanted to run this for Theta GPU, which I have a separate recipe for, I would run docker build. Same with my repo address, but then in this case, my tag, I'm going to use the tag Theta GPU. So this will be a different image tagged with Theta GPU. So it's not latest. I guess I should have tagged this one Theta KNL maybe to make it clearer. Again, these tags can be anything. And since I want it to use the Theta GPU Docker file recipe, I'm going to specify that with -f. So that just means don't look at the default Docker file, use this one, and then build in this directory. Okay. And so once those have finished building, which I give an example here where I'm building the Theta on my local MacBook with Docker installed. On the MacBook, the Docker runs as a desktop application, so you have to make sure you have the desktop dashboard running. Otherwise Docker doesn't work. So you can see the first step where I build. So I'm building for Theta. I'm down in the containers directory. And it goes through, grabs the Ubuntu image, and then it's going to run the build command. Now, I had run this previously, and you can see this cache. It caches things, so if you build the same exact recipe twice, the second time it doesn't do it again. It just says, "Hey, I already have all this stuff sitting here. I'm just going to use it again." Obviously, if you delete the Docker cache, then it's going to rebuild it. The first time I ran this ran for a very long time because it had to download mpitch and then build it from scratch. And then the second command you see run is the push command. So the Docker push is what pushes it to the Docker hub. So if I go to hub.docker, I have to sign in. Does it log me out? Oh, okay, there we go. So you can see a list of the repos here, and then you can see the ALCF example one that I produced, and you can see these tags that I've included. And so you can see the tags that I've pushed. Now that I have those up in Docker Hub, they've been uploaded to the web. Now I can log into Theta. On the login node, I can just run Singularity build, some image name, can really be anything. I tend to use S image, so Singularity image. Some people use SIF, which is the technical SIF, the Singularity image format, I think. So anyway, and then I give it the address to my image. So Docker : // and then my username and then the repo name. And I forgot my tag here. I should have : latest. I believe that if you forget the tag, it automatically gets : latest. So this will create this image file. And once you have that, you can actually, on the login node, I'm going to switch my share here. I'm going to switch it to my terminal. I'm just going to play around here for a moment so you can see. So you should be able to see I'm in the containers and I have my Docker Theta GPU and Theta compilations. And if I run Singularity exec, and I'm going to use my Theta one, and I can just do ls/, I can get a directory listing in the slash area. And then remember, we put our software down in user source. And so you can see my binary build and my Python example is down there. You might recall we put MPI in the mpitch directory. So you can see mpitch built in there. So here I'm running Singularity to kind of inspect my, my container or my image. And I think I can also run bash, which puts me in the environment itself. So you can poke around this way. I don't think you can change anything without being root on the login node. So anything that you do here is just for inspection and for your own interest. It's not going to change anything in the image itself. So just be aware of that. And then from here, I can submit jobs. So I can go into the Theta directory. You can actually see some previous jobs that I've run. And I can run qsub. And actually, let me see, what are we using for the training? Not node list. Is it training, just the training queue? Let's see what our reservation is called. Let's see, inactive. Ah, there we go. So here's our queue name. That was the show res command, which is handy. So then I'm going to use queue name comp perf workshop. And for me, I'm going to use the project data science because I'm part of the data science group. And then I'm going to type in the job submission, and then I'm going to tell it which image that I want to use. I want to use my Docker Theta image, and that will submit. Let's take a look at this job script real quick. So this is just an example. It's going to run a 2-node job with 10 minutes. Actually, yep. And I have set up, in this case, I'm going to run 4 ranks, MPI ranks per node. The first thing on the command line is my container name, so I want to save that. It's important in this case to swap out the module cray impitch with the cray impitch ABI. So ABI stands for application binary independent. So this means that I can build with generic versions of mpitch like I did inside my container environment, you might remember. And my program will know how to use this library the same way it did the other one that it was built with. So it just makes it a generic interface, whereas cray impitch probably has some custom cray changes that we don't want, we're not going to be able to use in this situation. I also have some additional paths here that I want to include in my LD library path. These are locations on the Theta file system that have libraries coming from cray impitch ABI and other cray specific libraries that we need to run our applications. And then last, the next step, I'm going to add to the Singularities LD library path. So by default, Singularity, when it runs a container, uses the containers LD library path. And in this case, I want to add these paths so that I get the proper MPI. So to update the LD library path or path inside of a Singularity container, I have to specifically set this Singularity env underscore LD library path. So this overrides the LD library path that otherwise was in my container. It's only for these two very specific. Otherwise, every other environment variable that's in my environment prior to running Singularity will be available inside my container. It's just because these are, typically such special, environment variables that Singularity wants you to be extra specific when you want to override those. So we also have some bindings. So these are binding outside folders from the Theta file system into our container. So it's just making them available. So inside the container, I want /opt to be there so that all of these paths are available, and /etc alternatives, because we also have some libraries in here that are dependent on libraries down in here. And next, I can run my applications inside my container. So we have the usual AP run commands for launching an MPI application on Theta. Remember, inside this script, we're running on the Theta mom node, not on a worker node. And then that is going to call Singularity exec. It's going to include my bindings from here and my container name, which I passed on the command line, you might remember. And then I want to call inside my container the MPI hello world from the C compilation and the MPI hello world with Python. Let's see, did my job complete? Looks like this was my job ID, and these are the output files. So let's take a look. Okay, looks good. So I ran on 2 nodes, you'll remember, with 4 ranks per node. So that's 2 times 4 is 8. Got my 8 processes with 0 to 7 ranks. And I see host names. I can see that my ranks were properly distributed across the hosts, so that's good. So that was the example for Theta. For Theta GPU, I wanted to point out in the Docker recipe, instead of compiling mpitch, so we run mpitch on Theta KNLs. On Theta GPU, we run OpenMPI instead of mpitch. I believe this was due to compatibility with the NVIDIA drivers for communication, but in any case, there was a technical reason why we decided to do that. But that means that in our Docker recipe, instead of installing mpitch, I want to install OpenMPI. So that's the only big change between the 2 recipes. So I install OpenMPI. I remember to include my special build flags. In fact, OpenMPI I found had 1 extra one. So those are documented there for you guys. And if you build that, you'll get a container that you can run on Theta GPU, which is right here. And so you'll see again on the command line, I can run and do an ls for OpenMPI and see that in the Theta GPU case, we have OpenMPI installed there. And of course, we still have our user and source code directory, which has been compiled. Okay. To run this one, we would need to go into the Theta GPU directory. We would need to swap out our Cobalt. So we want to module load Cobalt. GPU. There we go. And then I can do another Q sub. Q sub, what was it? Q sub, there we go. And instead of job submission, I stated GPU -SH and this image. Oh, sorry, not that. There must be a different one on here. Let's see. Training GPU, is that it? No. No. Oh, let's check. There we go. Training GPU. Okay, so that's queued up. So while we're waiting for that, there was one, oh, there is a difference in the job submission script. So maybe I'll say a little bit about that. In the, let me check. In the job submission script, it's a little bit different. We have to use MPI run instead of AP run. In this case, we provide a host file, which is provided by Cobalt's environment variables, telling how many total processes, how many total MPI processes, and how many processes per node. But for Singularity with NVIDIA devices, we want to include this --NV command, and this is there so that the CUDA drivers are passed through to the container environment. So, but again, we run the C++ example and the MPI example. Let's see, that's still queued up. Maybe I used the wrong.
We have a single GPU mode now, so.
Oh, everything's single GPU.
Yeah.
Okay, okay. Well, this is set up for 2 nodes because we wanted to test the MPI. So in any case, we'll delete that so it doesn't just sit there and run sometime later. But the point is, you'll see a similar output to what you saw before on Theta. Okay. And then that leaves the remaining step, which is building on, what is my time limit here? Let me look at the agenda real quick. I want to make sure.
We're still running 15 behind until 4 o'clock.
Oh, okay. So I had until 4 o'clock and now I'm 10 minutes late. Is that right? Yeah.
Did I read that right?
I think
Yes.
I'm already 10 minutes past. So in any case, you can also build for Theta GPU only. You can also directly build Singularity recipes, and we've included 2 here with extensions DEF. I include in the README under Theta GPU instructions on how to use these. They are very similar to the Docker. They pull in the exact same image from Docker, actually, and then they have a specific Singularity recipe structure. And you have to run those on the compute node. And like I said, that's only available on Theta GPU, not Theta KNL. But anyway, Ask